This lecture is on transformers and power transmission. So going back to Objective 3 on the Unit 8 overview, we've completed the first two in the last two classes, and now we're going to complete two more today. We're going to solve problems involving step-up and step-down transformers, and we're going to describe the use of transformers in an AC electric power distribution. Um, so in order to understand why AC actually is super useful for us, this is the key winner of this whole unit, I think, in terms of why it matters that we use AC. So I want to look at power loss during power transmission for a DC current and for an AC current, and then that's where we'll find out why AC is so useful for us in terms of a society. So in this problem, we're going to venture down and say, why does using a transformer to change the current and voltage that is being transmitted, how does that improve or not improve our the power loss in this transmission of power? So let's look at this coming from a non-ideal situation. The generators at a power station typically produce 100 megawatts of power at 30 kilovolts. A small town 100 kilometers from the power station requires that electrical power, which will be delivered via aluminum cables that have a total resistance across the 100 kilometers of 2.1 ohms. So a side note is that 2.1 ohms technically came from a calculation of the resistivity calculation, because it's aluminum wires have a certain resistivity, and we know that the resistance in those wires is proportional to the length of the wires. So as we get further away from this power station, our resistance is going to increase across the whole length of the wire. So this is the picture that we have. We have a power station with 30 kilovolts coming out, 100 megawatts, 2.1 ohms, and it's 30 kilovolts all the way down. Let's actually make that all the way down until it hits this transformer. And what a transformer has the ability to do using our alternating current is it has the ability to change the current or the voltage to make it useful for us. 30,000 volts is not useful. We would not want to have 30,000 volts coming out of our outlets. That would be dangerous. So we change it down to 220 volts to make it more reasonable. Though this is still not ideal, and let's find out why. So this town has the ability to step down the voltage. So this is a step down transformer, means it decreases the voltage from 30,000 volts to 220 volts. And if no change occurred to the voltage slash current until it reached the town, we want to calculate the power dissipated or lost in those 100 kilometer length of cables to the town. So let's find out what values we have. Well, we have a power of 100 megawatts. So 100 times 10 to the 6th watts. We have a voltage of 30,000. So 30 times 10 to the 3rd volts. And we have a resistance of 2.1 ohms. Since we already have the resistance, the 100 kilometers doesn't impact our problem solving. So we would want to look at our power dissipated equations, and we have two, and that's P equals V squared over R and I squared R. And there's a moment where I mentioned which one is more useful than the next. And in this case, this one's going to be more useful because when we look at the wire traveling to the town, those wires are in series, right? Because wires, connect to each other, and so that's going to be nicer because since it's in series, the current will stay constant. We don't have changing current. Really, this one doesn't work because this V is technically a change in voltage. So this 30,000 volts is not the change in voltage because we would have to find out the change in voltage lost in the wire. And if we're already finding the change in voltage lost, then we're already pretty much solving the problem. So it doesn't work. We'd have to do some calculation to find that, which might be tougher than you think because we don't know the resistance in the town. So that is not useful. So the P equals I squared R becomes your power loss equation. So this is your one, and of course it's in your data booklet. So this is the one we'll always use when we're talking about power loss in cables, especially traveling to a town or traveling some long distance. But we don't know the current yet. We have the resistance value in the wire, but we don't have the current. So we need to find our current. So P is equal to I times V. So I can go P divided by V to get my I, and that's going to get my current traveling out of the power station and across the wires, and I will get 100 times 10 to the 6th divided by 30 times 10 to the 3rd. Let's kind of move this over so it's kind of separated from the rest. And that is 3.33 times 10 to the 3rd amps, so about 3,300 amps. So we have our current. Now we can actually use our power loss equation. And that's 3.33 times 10 to the 3rd. That gets squared, and that's multiplied by 2.1. So in this equation, you can see how important the current is because it gets squared. So this is going to give us a rather large number, and 23.3 times 10 to the 6th watts, or 23.3 megawatts. So there's a power loss of 23 megawatts. It's almost 25% of all power that is trying to be transferred to the town. So you'd have to take that into account, right? That's another version of efficiency. So we want to make this a better system. And we know we can use a transformer to step down voltage. Well, we can also use a transformer to step up voltage. And the one thing that we want to recognize as we're doing this, as we're thinking this, is this transformer doesn't there is efficiency in the transformers, but it always transfers the same power. So 100 megawatts at the power station, there's some power loss here, right? 23.3. So you'd have something like 76.7 megawatts left. And then that means through the transformer, there's still 76.7 megawatts. So although our voltage is stepped down, that means that when it gets here, the current must increase to maintain the same power transfer. And then that current is pretty much split across all the houses in the towns. And that's why it isn't actually that dangerous, because there's only, even though there's a lot more current available to the town, it gets split in imagine that all the houses are kind of in parallel. Kind of a strange thinking, but that's the way we can think about it. So the next problem is, let's try to make this more, not the correct word, but efficient. Let's not have so much power loss. So the power station installs a transformer at the power station to step up the voltage, and it steps it up to 115 kilovolts, while still delivering the 100 megawatts of power due to power conservation or energy conservation. And so it still travels, and even though it looks a little shorter, this is still the 100 kilometers to the town. So nothing's really changing about the cables. The only thing that's changing is we're increasing the voltage to a voltage that's almost 4 times higher. Well, due to power conservation, right, the total power is still 100 megawatts. Well, now our voltage is 115 times 10 to the 3rd. So we want to find our new current, and since our voltage has almost quadrupled, then our current should be kind of quartered. So our current is still 100 times 10 to the 6th divided by 115 times 10 to the 3rd. And that gets us about 870 amps. Yeah, so it was 3,000, and now it's 870. And we can use our power loss is equal to I squared R, and that's equal to 870 squared. So it's been quartered, but because it's being squared, the power loss is going to be around 1/16 of its original value. So 870 squared times 2.1, and that gives us, what is that? About 1.6. 1 2 3 4 5 6 times 10 to the 6th. So oh, I'm sorry, I wrote watts. So it's still a lot of power, but that's 1.6 megawatts. And so we have taken this 23.3 megawatts, which is about 23% of the total power that was transferred to the town, and now only 1.6 megawatts has been extracted. So what started with 100, right here, power loss of 1.6, and then there's something like 98.4 here. And you still have the majority of the power at the town. And so we've decreased power loss by doing a step up voltage transformer to decrease the current and therefore decrease the power loss. All right, so that's the importance of the I squared R equation. That's why we know that a smaller current is going to decrease the power loss significantly due to the squared value in the equation. So let's start looking at what transformers are. So now we know that we can use transformers to benefit our society in transmitting power. Like imagine a time when we had DC power where we couldn't step down. And so if we wanted to send 100 megawatts of power across some distance, we would have large amounts of power loss. And they found out that even when they were building DC power stations, I'm pretty sure like you couldn't be further than 2 kilometers away from the power station, or else you wouldn't receive any power. So using alternating current and transformers has really benefited our society in giving everyone access to electricity. So a step up or step down transformers are used to increase or decrease the voltage while attempting to maintain the same power output as the input. And I do say that while attempting to maintain the same power output, because even though I've assumed these transformers above are ideal, we're going to eventually learn that there is issues in transformers and there's an efficiency inside the transformer itself. So the circuit symbol looks like this. This is technically 2 coils. So this is like a coil and there's another coil. And that's how we picture it. But what they really are is something that looks like this. Now this can be kind of a lot. So let's go through each part. We have our primary current right here and a primary voltage. So that's like the current and the voltage coming from the power station. And then there's this transformer. And in the transformer, in this shape, it's a square. There are primary windings. Now, as this current fluctuates, right, and goes, that's my current goes like this, we know that our magnetic flux also will fluctuate. And that, right, so if this is our current graph, like this, right, then we know our magnetic flux graph is going to be something like this. So it's also going to be oscillating back and forth, which means this magnetic flux will be going this way at one time, and then once it's changed from the positive to the negative, it's going to go backwards. And so it's going to go, the magnetic flux is just going to rotate right and then rotate left, and then rotate right and rotate left. And as that's happening, it's changing. And we know that changing magnetic flux produces a current. So over in this next, this right side, we would say, well, due to the amount of coils in this side, we will have some secondary current and some secondary voltage. And we call this IPVP, or sometimes we call this, like, you'll see it, I think, in our data booklet, it's EMF. They just like to use that symbol. And then some secondary current and secondary voltage is like transferred over to the right side. Depending on how many coils there are will depend on how much current and EMF is induced. So let's review this. So an alternating voltage occurs in the left side in the primary EMF. That alternating voltage produces an alternating current in the primary current wire. That alternating current induces a changing magnetic flux, as I showed by the graph and what we learned previously, and it oscillates left and right, clockwise, counterclockwise, clockwise, counterclockwise. Since there's a changing magnetic flux that's traveling through the core, then that's going to induce a voltage in the secondary EMF, and it's going to be in a alternating voltage as well. And then that secondary alternating voltage is going to produce an alternating current in the secondary wire. And so we need to see how the transformers step up or step down the voltage. And we need to assume that first it's 100% efficient. We have to go back to Faraday's law to say that we know that EMF is equal to N delta phi over delta t. There's a negative there. And we want, since there's different N's, we want to give them a name. So let's say this is like our primary and this is our primary. Now, if it's 100% efficient, then the changing magnetic flux in the primary coil is going to travel, and the secondary coil is also going to feel the same magnetic flux. So actually this delta phi over delta t isn't a primary secondary, it's equal for both. So I can also give it a EMF secondary is equal to a negative N secondary number of coils times delta phi over delta t. And I can do some substitution here, where if EP over NP is equal to delta phi over delta t, ES over NS, and sorry, there's a negative there, is equal to negative delta phi over delta t. The right side of the equations are equal. That means that EP over NP is equal to ES over NS. And specifically, it's shown in your data booklet like this. EP over ES is equal to NP over NS. And so that's telling you that the ratio of the voltage is equal to the ratio of the coils. So we can imagine then that in this situation, where we have more coils on the left side in our primary than we do on the right side, this is a step down transformer. And so this is the first relationship that we'll be thinking of, and I think it's the most important. But there's a second relationship that we want to reflect on, and that involves the current. So how does the current change depending on the number of coils? In order to do that, it's easier to see it in the perspective of P in equals P out if 100% efficient. So we have like IP times EMF, the primary current times the primary voltage, is equal to the secondary current times the secondary voltage. And so EP over ES is equal to IS over IP. And let's make this a little prettier. And so it's just, right, it's just inverse. The primaries and secondaries are inverse. So we can connect that over here and rewrite this as also it's equal to IS over IP. And this is actually what's in your data booklet. Now, you might not still feel super comfortable about what's actually happening, especially we haven't seen an animation or a video on this. In this video that I'm going to link in the YouTube detail, the details of this video is a great representation of what's occurring in a transformer. It shows all the different types of coil differences and how using the thought of energy conservation, of like assuming 100% efficiency, how the voltage and the current transfer from the left side to the right side. And it does it using these blocks of energy as if like it's carrying like 1 joule of energy, and how that transfers over. And it's a very, very good representation of the situation of transforming, stepping up or stepping down. So this is a must if you should be watching this video to make more sense of how transformers work. Now, the math isn't that hard. Similarly to kind of before, the math is like the easiest part of this. The concept's kind of the hardest part. So let's do an example first to kind of finish this up and see if we can make sense of these equations, and do they make sense in a mathematical way as well. So an example The primary coil of an ideal transformer is connected to an alternating supply rated at 230 volts. The transformer is designed to provide power for a lamp rated at 12 volts. Okay, so we need to step down, but it has 42 watts and 45 turns of wire on its secondary coil. Determine the number of turns of wire on the primary coil and the current from the supply for the lamp to operate at the normal brightness. So we need to find the turns of wire on the primary coil. So we need to find NP. We don't know what those are. And we want to find the current from the supply. So that sounds like the primary current as well. So we need to start identifying the variables that we have. Also, I made a quick fix on this. It should be 450 turns of wire, not 45. So that changed in the video. So we need to do our primary values first, and then I would do our secondary. I'd keep them separate. So we have our EP, that's 230 volts. Our IP, which we need to solve for, and our NP, which we need to solve for. And then there is like a power, primary power, sure, it's like PN. And we might not know what that is. Our secondary, we have an ES, an EMF of 12 volts. We have a secondary current. Oh, we don't know what that is. We have the number of coils is equal to 450 coils. And we have a power rated at 42 watts. And since we have 100% efficiency, that 42 watts is the same for the primary coil as well, because that's due to energy conservation. So first it says for the turns of wire on the primary coil. Well, I know it's a step down transformer because I'm going from 230 to 12. So I'm going to need that ratio to help me find out how many coils I need. So EP over ES, this is the equation from above, also in your data booklet, is equal to the ratio of primary to secondary coils. And we have 230 divided by 12 is equal to what we don't have divided by 450. And so 230 divided by 12 is about 19. So we're going to need about 19 times the amount of coils, as in the secondary. So that's, if I multiply 450 over, I get NP is equal to 8625 coils. Or turns, I should say. Turns is the correct terminology. Great. So check, our first one's checked. Let's put this right here. And we can solve for a primary current. So there's a few ways to go about this. You can use the equation above that's in your data booklet using the ratios. I like keeping it simple. So I would just know that, hey, my P primary is equal to my P secondary. And so I should have IP times VP, EMF P, is equal to my secondary current times my secondary EMF. But actually, I didn't need to do that because I know that's 42. That's 42 watts on the secondary. On the left side, I have 230. I have a current IP times 230, and that will end up solving for my primary current, and it should be, I believe, 0.183. Great. So yeah, simple math, but the concept and imagining what's happening is kind of the hard part. Now, we are 24 minutes in, but there's still one more thing we just need to talk about. We need to talk about how do transformers keep or maintain a low or a high efficiency, so low power loss. And there's a few things we need to look at because when there's a change in magnetic flux, that produces a current. Now, what's weird is actually, we haven't mentioned this, it actually produces a current inside of the core itself, inside of the iron. And that, due to Lenz's law, will actually oppose the magnetic flux change. So this is the reason why we have these laminations. So these laminations decrease the amount of what's called, we call them eddy currents. Eddy currents are like currents that are produced from changing magnetic flux, and that usually negatively affect our efficiency in transformers. Yes, in transformers. So we want to laminate the core. The first thing we do is laminate the core, and that's going to decrease eddy current effects. The eddy current effects are, due to Lenz's law, decreasing the magnetic flux that's transferring across. Now, choosing the core material, this material needs to be what's considered a soft metal so that it can be magnetized or demagnetized readily, and that helps just with the magnetic flux flow. So metals like iron do that. So a soft metal is important for the core. Now, choosing the wire material is kind of the obvious one, right? Low resistance in the wire, that's going to increase the efficiency. And then also, how do you design the core? Like in this case, it's a full-on just square. But are there other cores that you could design that will improve the transfer of the magnetic flux and decreases flux leakage, which is like the flux that does not travel to the other core? And these are the four things that a transformer can change to improve the efficiency. And that's all you really need to know. And that the efficiency is, of course, power from the secondary divided by power from the primary, which is the same thing as just P out over P in, right? That's the same. And we are done. So to wrap things up, there was a lot going on in this video. The power loss due to power transmission across cables of long distances is proportional to the square of the current. And so the current has a large impact on the loss of energy when transferring power. So we want to find ways to lower the current in the wire that's transferring this power to towns without losing the total power that's transferred. The way we do that is using transformers, and these transformers have step up and step down transformers. Those decrease the voltage, but due to power and energy conservation will increase the current using the proportionality as shown in the right here, which we already did the derivation for, and how you use those calculations to solve for these missing values, as well as what makes a transformer more efficient. So these four things are good to remember. Remember, before you end this, I know it's another video to watch, but this is a must do. I swear this is a great video to help support the learning in this Transformers lesson. All right, I will see you in class.